Hello, my pre-cal darlings. In this video, we are going to talk about evaluating a piecewise function, graphing a piecewise function, and we are also going to learn about the difference quotient. So let's get started here. This first problem I have is a function that is modeling the cost of renting a car as a function of mileage. So this is what I was reminding you guys in class, that we use function notation to give a description sometime of what we're working with. So this is the cost function, the cost as a function of mileage. That's why it's C of M. So function notation is nothing other than an opportunity to name a function and give it, like in this case, a little personality. This cost function is a piecewise function. And this is not really logical these days because most car rentals are based on days, and most of the time the mileage is unlimited. But for our purposes, I thought you could easily understand this. So notice that the domain is broken into three categories over here. And yes, M is for mileage. So if you rent a car and we have a flat fee of $100, and then you're going to pay 25 cents per mile if you drive between 0 and 500 miles. If you drive between 500 and 750 miles, you're going to pay 20 cents per mile. If you drive between 750 and 1,000, you're going to pay 15 cents per mile. But the flat fee of $100 stays the same. So this is a piecewise cost function. We're just evaluating here. So if we want C of 200, you just have to see, okay, well, which slice of the domain does 200 live in? It lives in this first slice. So this is why we use the first function in the piecewise function. So C of 200 is 100 plus 0.25 times 200. Of course, 25% of 200 is 50. 100 plus 50 is $150. So the cost of renting the car and driving it 200 miles is $150. Next, we've got 500 miles. Now, think about it. 500, I chose 500 because you need to think about, well, which piece of the domain does this live in? If you drive exactly equal to 500 miles, you're going to use the first function again because M is less than or equal to 500 here. In the second piece, M is strictly greater than 500. So let's plug that in. 100 plus 0.25 times 500. 500 divided by 4 is 125. So 25% of 500, 125. Wait, yep, that's right. So 100 plus 125, therefore that is $225. So if you drive 500 miles exactly, it's 225. Now, I thought it would be interesting because since we moved to the next option at above strictly greater than 500, what would it be for 502? It would be 100 plus 0.20 times 502. So we can see that we're getting a better rate if we drive more miles. So 0.2 times 502, that's 100.4. So what we're seeing here is that we were better off just driving 2 more miles because now that is only $200.40. $200.40 because we went to a cheaper rate. And if we drive even more miles, we're going to get an even better rate, another nickel off per mile. So that is going to be 100 plus 0.15 times 800. So that is 100 plus, so 15% times 800 is 120, and that is $220. So you can see it's a substantial savings. It's even cheaper to go 800 miles. That's why this particular piecewise function is not very logical. Now we're going to graph a piecewise function. And the first step that I like to take to graph a piecewise function is to use a highlighter and mark the lines of demarcation according to the breaks in the domain. So let's start with the first one. We're going to put an auxiliary line at x is less than or equal to -3, because that's where there's going to be a break in this piecewise function. So first, and remember, an auxiliary line is not technically part of the graph, but that's why it's given in a dashed form, because if you make it solid, then it becomes part of the graph. The next special value is at +1. So I'm going to draw another auxiliary line here. And you can see what this is doing. This is breaking the graph into 3 different sections. So here's the first function, x plus 2. Here's the second function, at g of x equals 4. And here's the third piece of the domain, 1/2 x plus 4. So we're going to draw 3 different graphs in there. Start graphing. So sometimes, remember, an XY chart might be helpful. And also remember, an XY chart always works. So let's focus, and I'll even use my Post-it note to just cover up that part of the graph, because this first piece of the function only exists in this interval of the domain. X is less than or equal to -3, so over here. So let's plot some points where x is less than or equal to -3. So how about -3, -4, -5? This is a simple linear equation, so g of -3 is -1. G of -4 is -2. G of -5 is -3. Plot those points, back 3, down 1. And yes, it is solid because of the or equal to in this section of the piecewise function. -4, 2, and -5, 3. So what we've got happening here is that, and remember, all values less than or equal to -3. So this piece of the function is going to go just like that. All right, now let's cover that, because now we're going to be working in this second piece of the function. Now, if g of x equals 4, think about that. That's the same as y equals 4. That is a horizontal line, a constant function. So basically, in this section of the graph, y equals 4. But remember, it's a function. So if I'm going to come up and I am going to be plotting those points through there, it must be open here. But it's less than or equal to 1, so that is going to be closed at the x value 1. So that, of course, is a horizontal line, and I just drew it in with those points. Once again, remember, because of how the domain is given, x is strictly greater than -3. That's why it is open right up there. Next piece of the domain, everything greater than 1. Let's plug in a few values. And we're going to multiply by 1/2, so I'm only going to choose evens. How about 2? How about 4? How about 6? So g of 2, 1/2 of 2 is 1. 1 plus 4 is 5. Half of 4 is 2. 2 plus 4 is 6. Half of 6 is 3. 3 plus 4 is 7. So over 2 up 5. Over 4 up 6. See how the slope is not as steep? It's only a half now. Over 6 up 7. And this gets a little tricky. So notice that we're going to go there, but like what is happening in this space? Well, what if we plugged in a 1 into this function? If we said g of 1, well, it's equal to 4, right? But remember, this is strictly greater than 1. So we need to think about, what if we plugged in maybe like 1.01? 1.01 is larger than 1, so technically it would have to go into this piece of the function. G of 1.01. So that would be 0.5 times 1.01 plus 4.5 and some change. 4.505. So what I want you to see here is, yes, we have an open circle right there, and that is a continuation of that graph. Because there are no gaps in the domain here, therefore there will be no gaps in the domain in this graph. So let me zoom in one more time so you can see everything going on here in this graph. Open here, open there. If it's not open here and not open there, we would not pass the vertical line test. So think, think, think. That is a piecewise function. Now, next in this lesson, we start going into the difference quotient. And I've also included a link on the What's Happening page that is a very succinct description of where the difference quotient comes from. Please watch that video. I think it's only about 8 minutes. Now, here's a quick description of what the difference quotient is. It's an algebraic relationship that describes the rate at which a function changes. Honestly, ladies and gentlemen, you are very familiar with slope, all right? So the slope of a linear function is the same thing as the difference quotient, but what the difference quotient does is it is able to be applied to basically every single function, whether it's a line, whether it's a curve, whatnot. So that's why this is a much broader idea of a rate of change. So please, please, please watch the video that I have also posted on the What's Happening page. We're going to start evaluating the difference quotient for some following functions. Oh, and I would also be remiss if I did not let you in on some very valuable information that this is one of the very beginning skills that you are going to have for calculus, because this is the very beginning of taking derivatives of equations and functions. So this is something to definitely put in your back pocket because you will be using it later. You should memorize this. This is something we will be using again, so commit it. I'm going to write it on the top of my paper just so you can continue to see it. And as I said, please watch the other video that I have posted so you'll know where it comes from. So if this is our function, we are going to apply the difference quotient here. So this is going to be, okay, so remember, f of x is defined as 3x minus 5. So wherever we see x, we are going to have to plug in x plus h. So first of all, let's find f of x plus h, and I'm going to put it in brackets here. So 3 times x plus h minus 5, that's f of x plus h, minus, again, note my use of brackets here, and be reminded, you can never overuse grouping symbols. You can definitely underuse them, but you can't overuse them. So here's f of x plus h minus f of x all over h. So from here, we need to use the distributive property, following order of operations, and we are going to simplify this. So going to distribute here first, which is going to give us 3x plus 3h minus 5 minus the 3x minus 5 all over h. I'm going to move to the right. So we got to distribute again this -1 right there. So that is going to be, and I'm going to be able to lose the brackets right now, 3x plus 3h minus 5 minus 3x plus 5 all over h. And the magic is about to happen right now, because 3x minus 3x will cancel, a -5 and a +5 will cancel, and we end up with simply 3h over h, which reduces to 3. This is a linear function, and the difference quotient results in a constant value of 3. We're going to see something a little different on the next one. The next one is not a linear function. This next one is a quadratic function, and it's in terms of g, but just because it's in terms of g doesn't change anything. The difference quotient here, just think of it simply as g of x plus h minus g of x all over h. We're still going to apply the difference quotient in the same manner. Remember, the g is just the name of the function. It doesn't change the value or anything else like that. So first, let's find g of x plus h. Once again, I'm going to put it in brackets. So here goes. 2 times g of x plus h. Everywhere we see x, we're plugging in x plus h. So that is x plus h squared minus x plus h. Once again, you need grouping symbols here in order to maintain some control over these negative signs. Plus 3 minus g of x, which is 2x squared minus x plus 3. This is just a straight substitution here, all over h. So I will move this up so we can focus on just simplifying here. Follow order of operations, which means we've got to take care of that exponent first and square that quantity that's inside. So that's 2 times x squared. Remember, you've got x plus h times x plus h. We're squaring a binomial. We get a perfect square trinomial of x squared plus 2xh plus h squared. If you don't believe me, multiply it out. Check it for yourself. Minus x plus h plus the 3. Still working inside this first bracket. And I'm taking it a step by step. So hopefully everybody can follow. Following order of operations, we're now going to distribute the 2. We also need to distribute that negative sign. And we need to distribute that negative sign. Here goes. I am able to lose those parentheses now. Whoop. Oh, yep, nope, good. I'm able to lose these brackets. I could have lost those. I'll cover them up with the magic tape next. Negative 1 times 2, negative 2x, negative times a negative, plus x, negative 3. So yeah, all over the h. This is no shortcuts here, ladies and gentlemen. But yes, I can get rid of the brackets. I really don't need them anymore because there's nothing that's getting distributed there. Okay, so now let's start hunting for like terms. So 2x squared, negative 2x squared. Goodbye. We've got, what else do we have? A negative x and a positive x. Goodbye. We've got a plus 3 and a minus 3. Goodbye. And now all that remains is, and I'm going to try to get this in a descending order here. So let's put 2h squared. And then we've got plus 4xh minus h all over h. So we've got the common factor of h all the way through, and it's going to reduce by 1 power of h. And this final simplified difference quotient, so that 1h cancels with 1 power there, leaving 2h. That h cancels with that h, leaving 4x. Negative h over h is a negative 1. So that is an answer. We could also say, if we wanted to put this linear part first, 4x minus 1 plus the 2h, that is the simplified difference quotient.